Right. Okay. Hi, I'm Sarah Harris. I'm part of a team at the University of Kent working on a Rust compiler for Morello. We have a port of version 1.56 for Cherry BSD, and we're hoping to update it soon to a newer version. The compiler and standard library work, and we've run over 100,000 lines of benchmarks from open source projects with it. Source and binaries are available. Our website's in the slides if you want it. So things I'm going to talk about, briefly why Rust, but like you probably have a good idea of this. And then I'm going to go through some highlights of the challenges we encountered while we were working on the port. So this is stuff about some types, usize, some partial evaluation stuff, const expressions, some fallout from that in data type sizes, and then some of the sort of technical awkwardness that comes up with vtables and panicking. So very briefly, just talk about Rust and why we're interested in this. So like there's a good chance everybody here knows what Rust is and why it's interesting, but just briefly, so it's a modern language. It's seeing quite a bit of popularity at the moment, and it has a lot of focus on safety and memory safety in particular. So this sort of kind of makes a logical match for Cherry. In particular, I've got this quick example program here. So you can call into C from Rust. To do this, you have to use an unsafe section. So this, where in most of Rust code, you have a bunch of protections from the language. Unsafe gives you a way to bypass these. This lets you do a few things, and that includes calling into other languages with weaker safety guarantees like C. So if we imagine that I've got a function from a C library here, perhaps isn't very trusted, and we want to pass some data to it from Rust. Normally, the C code can do anything it likes, but if we run this on a Cherry system, at the point that Rust's normal safety guarantees end, when we enter this unsafe section, we're then covered by the Cherry hardware. So we think this is quite a nice sort of combination of things. Cherry's guarantees are slightly different, but we think this still gives you quite good safety properties. So the journey to make this happen, sort of the big central problem that comes up is a type in Rust called usize. So this is an unsigned integer type, and as per the standard library documentation, usize is the pointer-sized integer type, and this is coming from a language designed sort of for x86 and ARM sort of conventional architectures, where a pointer is just an address. So this kind of assumes that a pointer is just going to be an address. So saying an integer type of the same size is nice and simple, because you end up with an integer just the same size as a pointer. You can put pointers in it, you can do arithmetic, you can do what you like. Clearly, this gets more complicated on Cherry because a capability has a bunch of data in it that isn't just the address. So you can say, okay, usize is the size of a capability, but if your code makes assumptions like I can cast from a pointer to a usize and do some arithmetic and cast back again, this can get complicated. So there are a couple of different ways you can deal with this. You can make usize 64-bit or 128-bit, or maybe do something a bit stranger. We've gone for 64-bit because we think this is the best trade-off. So we end up with something like this diagram at the bottom here. So capabilities end up being Rust's pointer type, which ends up being 128 bits wide, and it has the entire capability metadata in it. Usize ends up being 64 bits wide, so it's just the address component at the beginning of the capability. And then there are some sort of other implications of this. So we're currently defining uint pointer t, where we need it for compatibility to be capability sized. This is sort of an open area of discussion with the community, so it's complicated. There are implications of all of these different options, like none of these solutions is a nice, clean solution, really. All of them have the limitations. So most of the rest of the things I'm going to talk about are kind of fallout from this, one way or another. So sort of the first interesting thing we run into is Rust has this mechanism called a const expression. So you can declare, so as a quick example here, you can declare a value and it's constant throughout execution. These are interesting because they're computed at compile time. So this is kind of partial evaluation sort of stuff. And you can do like reasonably complicated things with this. This supports a reasonably large subset of Rust and I think an increasingly large subset of Rust. So you can do like arithmetic and you think, yeah, and you can call functions and things in here. So you can do quite complicated things. Because these values sort of get manipulated at compile time and then passed on to the program to be used at runtime, any memory layout needs to line up. So if we declare, so as second part of this example, if we declare a struct type, which has several different fields in it, and one of them is a pointer, for example, and then we use this in a const expression, the memory layout of this data will have to match up with the way it's going to look at runtime. So on Morello, where pointers are capabilities, the gap for this field here needs to be of the same size, both during compilation and at runtime. So this sort of gives us an interesting problem because the compiler needs to be aware of this, but we don't necessarily want to re-implement all of the semantics of capabilities inside the compiler. So our current solution to this is that we just leave gaps where the capability metadata is during compilation, and this gets filled in by runtime. So you end up with a layout inside the compiler that looks a bit like this example at the bottom, and then it lines up nicely at runtime with how it looks on Morello. To do this, we need some extra information. So the compiler, without any modifications, keeps track of the sizes of data during compilation, and it keeps track of this as one value called size. To be able to do these manipulations that involve metadata, we actually need two sizes for like various values we're manipulating. So the single size value becomes a data size and a memory size. And then all of the sort of memory layout, data structure layout logic has to be made aware of this. And these size values have to be given for all of the data that we're manipulating in the compiler. This is a sort of conceptually quite simple change, but in practice, this actually touches a huge amount of the compiler, and it's been quite a lot of the work that we've done. So by a rough count, this touches about 230 different source files, and there's sort of a quick and incomplete list of different important data types inside the compiler that this affects, and there's quite a few of them. Like, this was quite a lot of work to implement. So this sort of size stuff continues to have different sort of effects throughout the compiler and the language. Another place that this shows up is vtables. This is kind of interesting because this is a place where the compiler kind of explicitly conflates the size of usize and the size of a pointer, which is sort of as per the established definition. This is reasonable. But of course, because of the changes we've made, this is a bit of a problem. So vtables become a thing in Rust because you can have these situations where you want to have a type that isn't completely known at runtime. So in this example, I declare sort of an interface called data trait, and this just says whatever type this is going to be is going to have a function called reticulate. And then I can write a function with it, and this function will take a reference to a value to operate on, but all we know about the type is that it will implement this interface, and what type that is can vary at runtime. This is dynamic dispatch. So this reference to data needs to include both the pointer to the actual value itself and then an additional pointer to some extra information about where to find the methods that are attached to it. So what the specific implementation of reticulate is going to be. And in Rust, this is implemented by vtables. So the second pointer is a pointer to a vtable, and they look something a bit like this diagram. So they're an array of fixed-sized slots with a bunch of different stuff in them. There's some data that's always present up at the beginning, and this is a function for handling deallocation, and then some size information, which is just numbers. Because on sort of established targets, usize and pointer are the same size, the compiler just assumes that all of these slots are usize sized, which makes the arithmetic to access this list of stuff nice and simple. Unfortunately, on Morello, this is no longer true, and we need this to store both pointers to methods and also these numeric values. So the simple thing to do is just introduce gaps after the numeric values. So you end up with sort of this couple of holes in the always present data. This is kind of nice because it means we don't have to touch too much code. We can just update the way that the vtable layout is calculated in the compiler. None of the runtime stuff needs to know about this. This has nice limited impact on the rest of the language. So other sort of kind of awkward places that these effects turn up. The standard library provides a mechanism called panic. So this is normally quite a simple mechanism, like you call panic, an error is printed and a traceback, and the program terminates. This becomes more complicated in examples like this, because the standard library provides a mechanism for catching panics. And now they start to look a lot like a C++ exception, because you can initiate a panic and then some code further up the stack can catch the panic and then continue normal execution. And actually find that the implementation of this borrows quite heavily from the C++ implementation. So underneath this, this is reusing a bunch of bits of LLVM and some other things that already exist for providing this in C++ and other languages. So the implementation of this mechanism basically comes down to having a table that maps from program counter addresses recovered from the stack, and then provides a lookup from the address of the code being executed to information about whether it's a handler for exceptions. So we end up with, from this like little example program, if we run that, we end up with a stack that looks something like this. So panic happens, and that's happening inside the function called fatal, and then that's being called by the standard library handler mechanism. And the handler mechanism will be registered as a handler, so that when the exception handling infrastructure walks back up the stack from where the panic happened, it will find this handler, and then normal execution can be resumed. This creates some technical problems because this is encoded using effectively dwarf debugging data. And Morello actually has its own format for this particular entry in the debugging information. In C++, there's already an implementation of the reader that's used at runtime to extract this information. But in Rust, there's an entirely custom reader for this information. So we've had to make modifications to the standard library and port across the Morello extensions for reading from these data tables. If you don't do this, you get very, very messy crashes. This was quite a lot of work to figure out. Like, the changes themselves are actually quite small, but in figuring out what was going on took, I don't know, weeks at least. So yeah, this is just sort of highlights from what it looks like porting Rust to Morello. We have currently a Rust 1.56 compiler. We're working on 1.72. Updates would be nice. We can target CHERIBSD running on Morello. We have a working standard library. Our website is here. You can get source binaries, some other information, and there's some more details about this in an eCoot paper that we published earlier this year. So thank you, and if we've got time for questions, I can take questions, hopefully.
Hey, that's great. Thank you very much. We do have a bit of time for questions. I will try and deliver a microphone to you so that Sarah can hear questions. Questions?
Hiya. Do you reckon it's possible in the future to have a edition of Rust where the size and pointer are different lengths to get rid of these gaps in future editions and then have the backwards compatibility with gaps?
So are we talking about gaps during partial evaluation, or are we talking about gaps in vtables?
Sorry, I guess both, but that's not the important part. I guess the real question is, do you reckon we could have a future edition of Rust where the size, the address space and pointer size aren't conflated?
So, like, there are some open questions, I guess, about how to deal with the use size and pointers, like sizes of pointers and sizes of use size thing. There's a solution that someone else has written about already, where you make use size 128 bits wide, and then you can just sort of freely move pointers into that and back out again without losing validity tags and so on. But that then means that there are a lot of situations where use size is used for things that it doesn't need to store pointers. Like, I would, I can't remember if I have any good hard numbers on this, but at least my gut feel is that in the vast majority of cases, use size is being used for things like array indexing, where it just needs to be an integer. It doesn't need to be big enough for pointers. So making it big enough is really inefficient and causes a bunch of problems. So while that's sort of a nice solution because you don't need any of this weird gap shenanigan, the inefficiency is probably unacceptable. So yeah, there are a few ways you can go. All of them have awkward trade-offs. The gap thing itself, you might, if you made much deeper changes to the language, you might be able to do this more efficiently, I guess. I'd have to think about it a bit harder. We were interested in not making huge changes inside the compiler because it would be nice if we can get some of these changes upstreamed at some point. But it might be something that somebody can explore, I guess.
I have a quick supplementary question.
Mm-hmm.
I kind of imagine that those different usages of usize might be detectable by not too fancy static analysis. And one could then, suggest code porting changes to split that type into two.
Yes. So there are some lints available in recent versions of the compiler that you can turn on which try to detect casts between pointers and usize, which are sort of useful for some of this. There's been some talk about whether usize should actually be split into like an indexing type and a pointer manipulation type and things like this. They end up sort of having implications for the language, and it's a bit unwieldy. I don't think anyone's very keen on those solutions, but they've definitely been talked about.
Yeah. Okay. Any other questions quickly? Peng.
Hello. Does Rust exception handling use lib unwind to do the unwinding, or is it using a custom mechanism?
Yeah, the panic handling mechanism is lib unwind, and there's some moderately involved code in the standard library that sort of provides all the glue that you need for that to work properly.
Okay.
And that's the
Are
bit
you using
modify.
the lib unwind that's been ported to Morello that's also working with C++, or did you modify that yourself?
Yes, I think we are.
Okay.
I don't think we've needed to make any changes to lib unwind. So I think we're just using the one that's part of Morello LLVM.
Okay, thank you very much.